Hello students, on today we discuss about the reaction of phenol. Under the reaction of phenol, one of the most important reaction here is Reimer-Tiemann reaction in your syllabus. So in Reimer-Tiemann reaction, we convert phenol from its corresponding aldehyde, that is orthohydroxybenzaldehyde and parahydroxybenzaldehyde. The common name of orthohydroxybenzaldehyde is salicylaldehyde. This is around 80% of the product. So this is the major product, and parahydroxybenzaldehyde is about 20% of the product. So this is the minor product. The reagent for this reaction is used chloroform and a strong base. Here sodium hydroxide or potassium hydroxide is used as a base. So first of all, the reactant of this Reimer-Tiemann reaction is phenol. The product that is formed by this reaction is orthohydroxybenzaldehyde or salicylaldehyde in 80% and parahydroxybenzaldehyde is about 20%, that is the minor product. And the reagent that is used for this reaction is chloroform and a base. Here NaOH or KOH act as a base. The condition of this reaction is 70 degrees centigrade temperature, and we have to reflect the reactant to get the product. Here the main important question is why orthohydroxybenzaldehyde, that is salicylaldehyde, is the main product, and why parahydroxybenzaldehyde is a minor product. Because in orthohydroxybenzaldehyde there is a intramolecular, I repeatedly say, that is the intramolecular hydrogen bonding are present in orthohydroxybenzaldehyde, and this is kinetically controlled product. Kinetically controlled product. That's why it formed for huge amount. And in parahydroxybenzaldehyde, here intermolecular hydrogen bonding is present. So in your exam, if there is some questions for the conversation regarding phenol to OH and chloroform, it should be salicylaldehyde. Okay, but the another thing of this reaction, if we use carbon tetrachloride, that is CCl4, instead of chloroform of this reaction, that is the presence of base, use carbon tetrachloride CCl4 instead of chloroform, we get salicylic acid. Instead of salicylaldehyde, we get salicylic acid. We get salicylic acid. Okay, so this is an aromatic electrophilic substitution reaction. Let's we see what is the mechanism of this reaction. Let's go through the mechanism. Step 1. First of all, CHCl3 chloroform react with a base and form CCl2. Okay. Step 2. Step 2. This is phenol react with OH minus and form phenoxide anion. Phenoxide anion. This is phenoxide. Phenoxide anion. Step 3. This phenoxide anion go through the resonance Now the step 4, this phenoxide anion react with CCl2 and form CH3. By react with acidified reaction, it forms CHO. This is the actual mechanism of this reaction. So this is the actual mechanism of this reaction, and it is called salicylic. It is called salicylic from the phenol. Okay. The another important reaction in our syllabus is Caterman aldehyde synthesis. Caterman aldehyde synthesis. What is the reaction of this Caterman aldehyde synthesis? Let's take. Caterman aldehyde synthesis. In Caterman aldehyde synthesis, we convert benzene or toluene. This is toluene. This is benzene. To its corresponding aldehyde. That is, from benzene to benzaldehyde, from toluene to orthomethyl benzaldehyde or paramethyl benzaldehyde. So here the reagent that is used for this Caterman aldehyde synthesis is hydrogen cyanide HCN in acid HCl hydrochloric acid in presence of aluminium chloride. And the temperature is 100 degrees centigrade. So here the reactant is benzene or toluene. Product benzaldehyde from benzene, and from toluene we get orthomethyl benzaldehyde or paramethyl benzaldehyde The reagent is HCN, that is hydrogen cyanide or cyanohydrin, plus HCl in a Lewis acid, here it is aluminium chloride, and the condition of this reaction is 100 degrees centigrade. So here benzene or toluene converted to its corresponding aldehyde, that is benzaldehyde and orthotoluene benzaldehyde, orthomethyl benzaldehyde or paramethyl benzaldehyde. Okay. Thank you.